Hello and welcome to this lesson video where we will learn about the properties of the main geotechnical materials, soil and rock. Specifically, we'll learn about the weight-volume relationships of typical geotechnical material and the categorization and types of geotechnical materials. A soil sample typically includes the particles of the soil solids and the voids in between. These voids can be completely empty or completely saturated with water, or in between, like the shown figure here. The soil is said to be dry when its voids are completely filled with air without any moist or water in the soil. For the sake of analyzing the soil sample and its weight-volume relationship, the soil sample can be simplified by clustering its three main ingredients. You can see in the right figure here how the solids, air, voids, and water are lumped together in three volumes. Now let's add some notations here. The left notations are for volume values. The right notations are for weight values. The total volume is made up of the volume of the solids and the volume of the voids. The volume of the void is the addition of the air volume and the water volume. In the dry case, the water volume will equal to 0 and the void's volume will be completely be filled with air, or VV will be equal to VA. In completely saturated soils, all voids are filled with water, or VV will equal to VW. On the right side, the total weight of the soil is the summation of its solids weight and the water weight. Of course, we can model the air here to be weightless, or the weight of the air is equal to 0. Now let's establish the standard weight-volume relationships for a soil sample. These relationships are formulas to calculate representative values of every unique soil sample related to its density, water, saturation, and porosity. The first relation, called the unit weight, is a typical density formula as the ratio between the soil weight or to its volume. The unit weight is also known as the bulk density of wet density, as the total weight includes the weight of both water and the solids. You can see here. The unit weight or density is measured in pound per cubic feet or kilogram per cubic meter. The second relation is also a density formula, but is calculated for the dry state of the soil by considering only its solid weight, WS. The third relation models the specific gravity of the soil, which is the dimensionless value as the ratio between the solids density and the water density. The solids density equals to the ratio of the weight and volume of the solids part, WS VS. The water density, gamma W, is a standard value that is dependent on the surrounding temperature. For example, at 39 degrees Fahrenheit, the water density equals to 1 grams per cubic centimeters, or 62.424 pounds per cubic feet. The fourth relation quantifies the water content of the soil as the ratio between the water weight, WW, and the solids weight in the soil sample, WS. A dry soil sample will have a 0 water content value. The fifth and sixth relationships are used to quantify how porous or spongy the soil is. The void ratio is calculated by dividing the void's volume, VV, over the solid's volume, VS. The porosity of the soil is calculated by dividing its void's volume, VV, over its total volume, V. For a sample of just a solid boulder, its porosity will be 0, as the boulder is made of a big mass of rock with 0 voids inside. Now let's move to the next part of our lesson, which is the categorization and types of geotechnical materials. Soil and rock are very heterogeneous materials. In their natural state, they are rarely uniform. This is why it's hard to predict the soil performance compared to other more homogeneous materials like steel and concrete. However, the ingredients of a geotechnical material can be categorized in 3 main types. First, organic soil is partly made of vegetation, which is the topsoil layer that exists naturally in a typical site. The soil has a spongy, unstable structure and cannot be used as a structural geotechnical material. As such, before the topsoil in a construction site is removed, before the work is done in a project, the topsoil in a construction site is removed to reach to a suitable soil that can be used in backfilling or retaining structures. Although organic soil is not used for structural purposes, it can be recycled and used as a top layer that splays on new grades or slopes to allow for quick growth of natural vegetations for the purpose of soil erosion control. Second, non-cohesive soil or granule soil includes gravel and sand, which have no shear strength due to the lack of the cohesion between the grains. So let's give an example by your childhood days on the beach, or even your grown-up days now, like me. When you build sandcastles, sand in itself is not stable material to form the walls of the sandcastle, as it tends to be stable at only small slopes of around 30 to 45 degrees. However, adding a little water generates some cohesion between the sand grains, which can help in making the sand stable at the higher slope angles. However, once the sand dries, the steep slope becomes weaker and subject to failure. Of course, the bigger the grains, more gravel than sand you can say, the less cohesion is achieved through water content. If well consolidated and confined, non-cohesive soils can form a foundation that's almost as stable as rock. Third, cohesive soils include silt and clay. This soil type is known by its small platy shaped grains that pass through small sieve sizes, especially standard sieve size number 200, like we'll see very soon. Such small grains result in a shear capacity that's much better than non-cohesive soils. It's possible to make a vertical cut in silts and clays, and it remains standing, unsupported, for some time. This cannot be done in dry sand. However, clay consists of very fine microscopic plates, like these plate-shaped particles, which hold water to increase their volume and release moisture to decrease their volume. So, special precautions need to be taken in the design of footings to resist or avoid the forces caused by shrinking and swelling of underneath soil made majorly of clay and silt. Although soil is not a homogeneous material, but its strength, performance, and construction properties can be predicted or estimated by classifying the soil composition using the Sieve Analysis and Atterberg limits. Depending on the soil type, Sieve Analysis is used to classify granular non-cohesive soils like gravel and sand, while Atterberg limits are used to classify cohesive soils, namely silt and clay. Sieve Analysis consists of shaking the soil through a set of sieves that have progressively smaller openings. The results of the sieve analysis are generally expressed in terms of percentage of total weight of soil that passes through different sizes of sieves. This table here shows the sieve size from the one with the biggest sieve hole, 3-inch, to the smallest sieve size, 0.053 millimeters. Boulders are any grains bigger than 3-inch, but any grains between 3-inch and sieve number 4 are considered gravel. Sands cover much wider range between sieve sizes number 6 and number 200. Fines and cohesive soils pass through sieve number 200 and are classified using Atterberg tests, not the sieve analysis. You can see here I'm using plural to refer to the different types of gravel and sand. The outcome of the sieve analysis of a soil sample is to develop its particle size distribution curve that can distinguish between different types of sands and different types of gravels. The shown particle size distribution curves correspond to 4 different soil samples. The horizontal logarithmic axis represents the sieve size, while the vertical axis represents the cumulative percentage of soil passing through a sieve size. 2 of the shown samples are for sand samples. SP, or poorly graded sand, and SW, or well-graded sand. You can see here that the well-graded sand is made up of a wide range of sand grain sizes, while the poorly graded sand, poorly graded sand, is made of mainly fine sand. You can see here by the smaller size of the sieve. The other 2 samples are for gravel samples, namely GW, well-graded gravel, and GP, or poorly graded gravel. The poorly graded gravel is made of only large, you can see here the change of cumulative weight passing, and small grains, with no smooth gradation in between, almost flat. Well-graded gravel, on the other hand, provide better strength performance as the different sizes of grains, as you see here, smooth transition, provide better interlocking and stability between the grains. Now moving to the cohesive soils, the Atterberg limits are a measure of a soil's ability to absorb and hold water. Water content significantly affects properties of silty and clay soils, unlike sand and gravel. Atterberg limits are used to classify fine-grained soils, namely clay and silt, and to quantify their plasticity. Soil plasticity is a degree to which puddled or reworked soil can be permanently deformed without rupturing. Atterberg limits are water content of the soil that mark the transitions between three main soil consistency states: semi-solid, plastic, and liquid. A semi-solid sample with low water content can be deformed, but it will crack under a small molding effort. Increasing water content by increasing the water content by adding more water to the soil, it becomes softer and transitions to plastic consistency. This results in the soil's ability to deform without cracking. Finally, increasing the water content will make the soil eventually become a viscous liquid object. As such, there are two Atterberg limits between these three soil consistency states. The liquid limit is the water content at which the transitions between the liquid and the plastic soil state, and the plastic limit is the water content that defines the lower limit of the plastic solid state. The American Association of State Highway and Transportation Officials, or AASHTO, developed standard tests to find the Atterberg limits of a soil sample, namely AASHTO T89 for finding the liquid limit and AASHTO T90 for finding the plastic limit. The detailed procedures for these standard tests are not described here, but I highly recommend that you check the many available online resources and videos to learn about these tests. The plasticity index, IP, is the numerical difference between the liquid limit and the plastic limit, which indicates the values of the water content range over which the soil remains plastic. Many mechanical properties of clays and silts can be correlated with the liquid limit and the plasticity index. This correlation has been expressed in the shown Casagrandi's plasticity chart for fine-grained soils, where the different cohesive soil types are shown relative to the liquid limit on the horizontal axis and the plasticity index on the vertical axis. The plasticity chart is divided into 6 sections that are divided by the oblique line A and 2 vertical lines at liquid limit 30% and liquid limit 50%. Each section of the chart characterizes a group of soils with well-defined mechanical characteristics. The 3 sections above line A are inorganic clays of low, medium, or high plasticity. These 3 sections below line A are inorganic silts of varying compressibility, organic silts, and organic clays. Note that the soils with a plasticity index lower than 10 and liquid limit lower than 20, which is this area here, are considered non-cohesive soils, like sand and gravel, which should be classified using the Sieve analysis, not Atterberg tests. We can make the following observations from the plasticity chart shown here. As the liquid limit of soils increases, the clay plasticity and soil compressibility increases. You can see here with these different categories, the plasticity increases to moving to the right. The compressibility is similar to plasticity, and it refers to the silt reaction and consistency when performing a standard shaking test near the plastic limit. In general, compressibility is approximately proportional to the plasticity index. The greater the plasticity index, Pi, the greater the compressibility of the soil. The second observation is, in general, the plasticity index is correlated with the amount of clay present in the soil sample. You can see here plasticity index at higher values is always that these three sections are all clays, while the silt are for below the line with lower plasticity index. Remember that the clay particles are finer and smaller than silt. As such, the plasticity index indicates the fineness of the soil and its capacity to change shape without altering its volume. A high PI, or plasticity index, indicates an excess of clay or colloids in the soil. This big table here shows overall classification of coarse-grained and fine-grained soils, which is called the Unified Soil Classification System, USCS. As you can see, the coarse-grained soils are classified based on their sieve analysis. We cover the well-graded, poorly graded, and there are for the gravel and the sand. On the other hand, the fine-grained soils are classified based on the Atterberg limits. You can see that soils with higher plasticity here have higher dry strength due to the higher cohesion forces between their small grains. Peat is highly organic material, which is not used in design and construction. This table shows the attributes of the different soil types, which are very important when considering which soil to use in different parts of a construction project. These main attributes are drainage, workability, subgrade suitability, and surfacing suitability. You can see the coarse-grained soils provide better drainage here than fine-grained soils. This is why they are used as bedding for underground utilities and foundations. The poorest drainage is shown by high plasticity clay. So the poorest high plasticity clay, this one here, which is the reason for using clay as the core of earthen dams, where the main concern is to retain the water behind the dam and not infiltrate through the earthen dam. In general, coarse-grained soils are the main type used as a structural material in most projects due to their good workability and suitability for subgrade and surfacing. We'll see in the other lessons the impact of the different soil classifications on their uses in civil engineering projects and their construction methods. For example, we'll learn how specific compaction equipment are recommended for different soil classifications. This is the end of this video, where you learned about the weight-volume relationship and the types of soils. The basic understanding of the soil material properties is a very critical knowledge to any civil and construction engineer. Thanks for watching, and have a good day.